welcome back to another Studying Works video. In this video we are going to cover the Intermediate Value Theorem, which is a fundamental theorem in calculus. Now, to understand the Intermediate Value Theorem, we are first going to have to understand continuity. So let's get into the video. To understand the Intermediate Value Theorem, we need to first understand continuity. What is it? Well, continuity is something that you probably addressed in your algebra classes, but it was just never really that important to where your teacher gave it a name. In calculus, it is that important. So I'm going to give an example of a continuous graph. As you can see on this graph, there are no stops, there are no holes, no nothing that is stopping the function from continuing. And that is a continuous graph. There are no stops in the function. But how can we find a continuous function just based on the function that we're given without a graph? Well, there are some simple criteria, and first off, if you have a polynomial function such as x squared, x cubed, and x to the fourth, those are always going to be continuous because there is nothing preventing it from continuing all the way to negative and positive infinity. But what about our piecewise functions, which we're going to go over in a bit, which can sometimes cause us to have holes or jumps or gaps that will cause us to not quite have a continuing function. So how can we check for that? First off, our first criterion is that the limit as x approaches c, which is a constant, has to exist. And what is c? What will c be? Well, most of the time when it asks you that, it is going to be asking you, is a function continuous at x equals blank? And that is the constant you are going to plug in for this limit. And sometimes it will ask you whether the function is continuous at all. And what you want to do for that is you want to go to points of concern, which we're going to go over in a bit, and it'll be a lot more simpler later in the video. The second part is that f of c must exist. And the final criteria is that the limit as x approaches our constant of f of x has to equal f of c. Meaning, for this function, f of c is right here. I can't just have my function going like this. That's not continuous. That wouldn't be a continuous function. In fact, this wouldn't even be a function because each input has to have exactly one output. But this is an example of a discontinuity. Although it's not a function, on the right we can see some discontinuous functions. So first we have a hole. So right here we can see it's continuous for all this time until we get to this hole, which means that f of x is probably undefined at x equals a, meaning that it cannot be a continuous function. So that's our hole. Next is our jump discontinuity. When we are starting here, we go here, we have an undefined point, and then we have our actual point, and we're coming back at x equals a. Now that, again, cannot be continuous, and that is for obvious reasons. It doesn't look continuous whatsoever. Now, our final one is a removable discontinuity, and I will go over why it's called that in a second. But you can see it's continuous for all this time, and then there's a hole, and we see that the actual value of f of a is down here. And so why is it called a removable discontinuity? It is called that because if we changed the y value of f of a right here, and we changed it to this y value right here, then we would have a continuous function, meaning it is removable, you can change it. Let's take a look at this practice problem. Check whether the function is continuous at x equals 4 and x equals 6. So we have our piecewise function right here, and right away, what would our point of concern be? Our point of concern is x equals 6, because that's where our function is changing. So if it just asked us if the function is continuous, we would have to check at our point of concern, which is x equals 6. That's where we're mostly concerned. But it's also asking us whether it's continuous at x equals 4. Already we know it will be, but how can we prove it? So let's take a look at this. First off, we want to find the limit as x approaches 4. Since this is a piecewise function, we want to pick the function that fits our criteria. So if x equals 4, we have to pick the function f of x equals 2x. So we have to find the limit of 2x as x approaches 4. And that would be 8. Next, we have to find f of 4. That's also 8. Finally, does our limit as x approaches 4 equal f of 4? If so, good, it's continuous, and we don't have to do anything else. You can just write it is continuous, or something of that sort. Now, let's check our actual point of concern for whether or not this function is continuous, which is x equals 6. So to find this limit, we can't just take our limit as x approaches 6 because we have two different functions. So we have to take the left-hand limit and the right-hand limit, which you should know from our previous limits video. If you don't know, make sure to watch that video. So first we have to take the left-hand limit, which would be 2x. And now we can see that that is 12. And now we have to take our right-hand limit, which in this case we would be using the function x minus 1 because we're coming from the right side, which is greater, and that would be 5. Since the limits are not equivalent, we already know that there's a discontinuity. But what kind of discontinuity is there? Well, let's check this on a graph. Usually you would just be able to tell this on your own, but I would like to represent this for you. So we have one that's approaching 12, and we have one that's approaching 5. What does this look like from our previous slide? You're right, this is a jump discontinuity, if you said that, because we can see that it's jumping. There is no continuous function here, and so it is discontinuous at x equals 6, meaning this function is not continuous at all. Now let's go over the main topic of our lesson, which is the intermediate value theorem. And it states, if f of x is continuous on the closed interval a comma b, and k is any number between f of a and f of b, then there is at least one number c in a comma b such that f of c equals k. Now that may seem like a lot, but it really isn't as complicated as it sounds. What does this mean? All it means is that if we have an interval of x values between a and b, there's some value c in the middle, and if we have f of a and f of b as our y values, there's some value k in the middle. So c comma k, there's some point there in between a comma f of a and b comma f of b. And that's all it's saying. And this has to be in a continuous function, which is why we had to learn continuity before. Now, this is really simple even in a problem, but it might show up on the AP test, which is why you have to be cautious of it and make sure you know what the intermediate value theorem is talking about. Now let's do a practice problem. Let's take a look at our practice problem. Explain why f of x has a 0 in the given interval and find the 0. F of x equals x cubed minus 2x squared plus 3x minus 6 in our given interval is -1, 3 inclusive. So usually we would have to prove continuity if this was a piecewise function or a function we weren't sure about, but since we know it's a polynomial function, I already told you polynomial functions are always continuous unless there's a constraint, we are fine. And so this function has to be continuous. Now that we know that it's continuous, how can we prove there's a 0? It's very simple. First, we need to find, we've got our x intervals right here, but now we need to find our y interval. So we have to plug in f of -1, and that is negative 12. And now f of 3, and that is 12. Now we have our x interval. I'm just going to keep this on the top so you don't get confused. And remember, this is all inclusive. Do not make the mistake of excluding any of these values. Now we have to prove that there's a 0. So how can we prove that with the information given? Now according to the intermediate value theorem, a continuous function has to have a point in between our x values and our y values. So we have our y values of negative 12 and positive 12. 0 is in between those two numbers, and so in a continuous function, it has to hit 0 at some point as our y value. And so that is what proves there is a 0. And usually you may have to write an explanation for that, and this is exactly what you should write. We have 0, which is between negative 12 and 12, meaning there has to be a 0. And that is a simple explanation you can give to get 100% on all of your FRQs. Now, how can we find that 0? It is really simple. We just set it equal to 0. And this is a little bit of algebra review for all of you. Now, we're given with this dilemma. We know if we set x squared plus 3 equal to 0, we'll get imaginary solutions, which is not what we want. So, we set x minus 2 equal to 0, and we get x equals 2. Now, that would be where our 0 is, 2, 0. But just in case, we know that our x value is in the interval given, but you always want to make sure that your y value is also in the given interval. I have made this mistake countless times, so you really shouldn't make my mistake. So, if we take f of 2, that is indeed equal to 0, which is in our y interval. Since it satisfies the x and y interval, that is our 0 in the given interval. And I already explained how you can get it using the IVT, or the Intermediate Value Theorem. Thank you for watching this video. It might be a bit of a long one, but it's really informative. And if you didn't understand the limits in this video, make sure to watch our limits video again. And I will see you in the next one.